All right, let's get going. All right, I'm gonna review a bunch of homework and then we'll do some new stuff. The calendar's going current. 3 assignments this week, kind of a heavy load, so the earlier you get started, the earlier you can get help from me. Quiz 3 here on Friday. I already made it. It's already going to be available, going to come available really early Friday. You only have Friday to do it, so just a reminder on that. Then actually in February plopped exam 1, so that's the 15th of February. Today's the 30th of January. So
was there a quiz last week?
Cruising right along, no quiz last week.
Okay, because I couldn't find one for the assignment.
Yeah, no quiz showed up on Friday. So
Okay,
we've had quiz 1, quiz 2, and now we'll have quiz 3. All right. So I'm going to go over 9, 10, 17, and 24 and 25. 24 and 25 is due at the end of day. So hopefully you've worked on it a little and maybe struggled with it. I know a few of you emailed me and had questions, so that's good. That's the process we want. Let's do 9 and 10. So again, I'm just going to work through these. If you guys got questions, you need to stop me. This is going back a little bit, still chapter 3, but the first part of chapter 3 was concurrent force systems. So this is concurrent, right? All the forces go through essentially one spot. Like you could extend them and it would go through one spot. So concurrent, and then 10 is also concurrent. And then I think, yeah, then we headed off into non-concurrent. So really good idea to get these like separated in your head because we attack them differently. We have 2 methods that we could attack this with. What's one of the methods? Trig. We're going to use trig on both methods. We want the resultant. So we want to turn this into the single force. No moments, right? Concurrent. So that's why I go back and forth, because you got to separate these. You're going to want to do moments now that we're doing moments, but before we did moments, we did concurrent force systems. How can I turn these 2 into one force? Find the resultant. So we could do, yeah, force triangle, and that would be log cosines. So force triangle means you add them together tip to tail, and you find the resultant. So if I did that, it would look something like, and you can add them in any order. I always redraw it, tend to always redraw it. When you redraw it, you want to keep the forces in their angular position. So I just took this and set it here. I'm going to take this and add to it, tip to tail. I'm going to try and match that angle. And it's much longer, like twice as long. Right? And then what we want to know is what closes it. And that's the resultant. So it says find the resultant, right? So that wasn't the first system that we learned, but we did learn this, that you can add them tip to tail. If there's only 2 of them, it's gonna make a triangle and then solve it out with non-right triangle strategies. So that's not sine, cosine, and tangent. That's sine law, cosine law, okay? So this is called the force triangle method, where you just add them together, tip to tail, and come up with R. How else could we do it? Think about the first method that we used. Tangent's a trig function, but what's the method? No, you can't. Nope. You got two methods to add vectors. You can do it with a forced triangle. What was the other method? We collected the X effects and we collected the Y effects. Component method, which means find the components of each force. Right? There's two components to every force. There is a Fx and a Fy of the 100. And there is a Fx and a Fy. Remember this? I hope so. That's the component method, where you just find the components and add them up, right? So you build these triangles, Fx, Fy of the 100, Fx, Fy of the 200. Find those two, add them, find these two, add them, right? These, you got to keep their signs straight. This is negative, this is positive, this is negative, this is negative, right? Once you get Fx and Fy, then you can go for the resultant. Yeah, Ben. Force. Force in the X. This is a force. 100 Newton force, right? So this is the X force for that vector, and this is the Y force for that vector. No, not function, never was. Force. Force in the X, force in the Y, right? This has two effects, X and Y. This has two effects, X and Y. All right, so either way, you can do it either way. This is a little simpler because we don't typically have to dig out all the angles, because in here we got two sides, we just need an angle, right? So we need an angle between the 100 and the 200, between 100 and 200. So that's this angle here. Actually, wouldn't be that hard to get, would it? Nope. You want to run tangent today, don't you? So if it's a straight line, how many degrees are in a straight line? 180, yeah. So I know that from here all the way over is 180. So subtract this one, 4113, and subtract the 37, and you're going to get this angle theta, which is this angle here. Then you could run the cosine law, as Timothy said. You're still drifting in the snow. Yeah, so this is just going to be 180 degrees minus 37 minus, what is this, 4113? How do I get rid of the 13? 16 divide 60 minutes. 60 minutes. So 13 60ths, which is 0.2166. So then 41 plus, so it's 412166. So what is that? Let's see here. $101.7833. So that's that angle. Right? And then we could do cosine law because we have side, angle, side. So if there's two forces, you can put them together to make a triangle, solve the triangle. If there's more than two forces, or if there's two, you can also find the X of that force, the Y, X and Y, and then add them up. It'll give you the same solution either way. On the exam, I could ask you to do it either way. I could say, by the forced triangle method, find the resultant. By the component method, find the resultant. Okay? So don't forget this stuff, even though we've gone to moments, right? We've moved on. You cannot forget the early stuff because that reappears in exams and all kinds of places. Strength of materials for the rest of your life. All right, so cosine law, what was that? That was like the c squared thing, right? I'm gonna write it r squared equals a squared plus b squared. That's these two sides. Minus the two sides. Cosine the angle opposite of whatever's here. Angle opposite is this 101.78 degrees. So then we got to run that. $241.17, actually 18, since this is a solution, newtons. So that's the magnitude. For the full answer, I'd have to go ahead and find an angle up here, which I could do with the sine law, because we need the magnitude and the direction and the sense, right? So then I could run the sine law to find that. This, call it alpha. Right? So the other thing you could do is once you get that and you have this magnitude, you got it. So component method. So this method right here, this is the more common method. You don't have to run this cosine law if that's not comfortable for you. This just says, okay, what are these x's? Add them up. What are these y's? Add them up, and then Pythagorean theorem, the solution. So we'll do that method on this one for practice. So this is your coarse triangle method. And then on 10, we'll do the component method. Same thing. They wanted to know the resultant, right? It's a concurrent system. The forces all go through the same spot. So there's no moments. It's going back in time here. We just want to know, hey, what's the single force that could replace these two? The component method says sum the forces in the x to get Rx, the resultant x effect. So what are all the forces in the x? Well, we have this one. It's all in the x. So I just put it in minus 200 because it's going that way, negative. And then I need this one, right? Because this force, the 200, has a Fy, force in the y direction, and a Fx, force in the x direction, right? So if I'm summing forces in the x, I want to sum up all the x effects. I got the 200. I need that one to go in this equation. So what do I do with this 3,5 thing? Say tangent. There you go. Boom, tangent, right? Because I know this side and this side, so I can get this angle. I'll call it alpha, right? And that's going to be, I'll just use tangent of alpha equals opposite 3/5. So alpha is going to equal, yeah, inverse tangent, 30.9637. So now that I have the angle, I can get this Fx. I know the hypotenuse is 200, right? So if I say, I'm going to use sine because x is opposite of this angle. So I'm going to go sine 30.9637 9637 equals 200 divided by, oh, sorry, not 200, opposite. Opposite is fx over hypotenuse is 200. So that's just working with that triangle. I found that angle, 30.9637. I want to find this x. That is opposite the angle. That should trigger in my brain sine. Then I just write the equation, sine of the angle, opposite over the hypotenuse, 200. So for fx. And this is fx of the 200, well, I'll call it 200 prime, 200, they're both 200, so that's confusing. Right? And I take 200 times the sine of that number. 102.89915 pounds. So here's a standard exam question that I ask. I might show you this problem and say, what is that? Like, what is that? What's the 102 mean? It is the X effect of this 200-pound force, right? Because the 200-pound force is at an angle. So it has X effect and Y effect. It wants to move this point to the left at 102 pounds. It wants to move this point down at whatever that is. I haven't calculated that yet. But that's what this vector, this 200-pound vector is doing. It's trying to move that point down and to the left. How much force? That much force. All right, so it's negative. It's pointing in the negative direction. So I'll put it in my equation, 102.89915. And all that equals this resultant X effect. It's going to be 302.89. I'm just adding these in my head. Negative. That's the X effect of this 200-pound force. Now I need the Y effect, and I need to calculate the Y's. So this one does have Y effect. It's just equal to 0. The only Y effect is this one from this 200-pound force. So yeah, it's adjacent to, so we're going to go cosine. And it's going to equal the adjacent side, Fy, that's this, over the hypotenuse 200. Oh, I lost my angle. 30.9637 cosine 200 times Fy equals 171.4986 pounds, and that's negative. It's going down. So this is the Y effect, right? So that's just all it is. We don't have to add anything to it. It's just, that's the Y effect of this 200-pound force.
How about that one part when you add in negative?
So that was the X. Why was there two forces in this equation? Yeah. Why is there two forces? Yeah, so we're adding up the X effects. So there's one there. That's an X effect. And there's one there. There's 2. How many are in the Y? 1, just this guy. This one doesn't have any Y effect. Okay. So Fy is actually, that is Ry, because there's no other forces, just this one Y force. So now the resultant, which means, okay, the goal was to get rid of these 2 and only have 1 force. That's why we collected the X effects and we collected the Y effects. So the X is 302. 302.89915, and the Y effect is 171.4986. And it's down, right? And this is our X and this is our Y. That's the X and Y effect of the resultant, this number we're trying to find, this vector. Right? So you sum up their components, sum the X's, sum the Y's. There's only one Y in this problem, but if there was 10 vectors, you'd have to do it 10 times. It'd make you nuts. But you get good at it. How do we find R? Have this and this, right? Pythagorean theorem, yep. Remember, R's in here somewhere now. That's where R is. And I know that RY is here, and I know RX goes that way. Remember, I can just take this, set it down here, build a triangle, the right triangle. I know 2 sides of the right triangle, 302 down here, 171 here. Pythagorean theorem will give it to me. The hypotenuse equals the 2 sides squared added together. .302, I lost my 302 number, that's a bummer. All right, I can take this number. Square it. 71. I get 348. 348.08. That's the magnitude. For the full answer, we'd need this angle here, angle to horizontal. Tangent will get you that. Sine will get you that. Cosine will get you that. You know all parts of the triangle now. So this is the force that can replace these 2. This is the effect that that point feels. So that's what we're doing. That's the goal, is to figure out, hey, what's the object feel? What's the point feel? I knew it was 200 this way and 200 that way, but I don't know what the combination of that is until I do this. Now I know, oh, 348 is the number I can design with, not 200 and 200, right? That doesn't work. I need the single force. This angle, if I wanted this angle, which is the common one that I want, remember that can just go there. So I just use inverse tangent, opposite adjacent. It's going to be the 171 divided by the 302 inverse tangent to get that. So I'll do that real quick because we really need that. We need the angle that R acts on. So 171.4986 and 302.89. Inverse tangent looks like it's about 29 degrees. So this little vector is like this, right? That gives me the sense down and to the left, and 29.52 degrees. So there's everything I need. It'd be nice if this point was named like point A, because then I could say at point A. So I have point of application, point A. I have line of action 2952. I have sense, that's this little arrowhead here. It's kind of down and to the left. And then I have magnitude 348.08. All the parts and pieces. Whew. Man, how fast we forget. I thought we had components down. No. Danner says we do not have components down, Coach Troy. All right, well, we need to get components down. So we're off. We're gonna do moments and then we're gonna do components again. So that might be helpful. We'll see. But we're just gonna keep going. 17. I think 17 was a moment problem. Not out of chapter 2. It's definitely out of chapter 3. 17 said the four forces shown have parallel lines of action. Remember, AB is perpendicular to the lines of action, so that's good. Everything's vertical. Determine the moment of each force with respect to point A. So here's the deal. Every force has 3 effects. Every force has an effect in the Y direction, effect in the left and right direction or X direction, and every force creates a rotation about a point. So they gave you the point, right? Point A. So they're doing that for you. At some point, you're going to choose yourself, but point A is right there. We know the equation for moment is what? Force times distance. And I put a little perpendicular in there just to remind me that it's the perpendicular distance. It's not any distance. It's the perpendicular distance. And we'll look, when we look at this one, we'll talk about that more. All right, so what's the moment of the 20 about point A? 5 feet. Yep. If I had to write it, it would be moment of the 20 about point A. Because remember, it's always. Oh, did I write it wrong? Oh, you're right. You're right. You're right. Thank you. Well, I didn't write the equation yet. So what is it? These are pounds. Force, what's the force? 20. What's the distance to point A? Yeah, 4 feet. Remember, it's perpendicular distance. So these are super easy, but that does make 90 degrees. So this is perpendicular. It is 4 feet. Force times distance. D stands for distance. But it's a perpendicular distance. And we fortunately have vertical forces and a horizontal surface. So that is perpendicular. If we had a force at an angle like this, then that is not perpendicular. You got more work to do. Okay. So what's this number? 80? And what's the units? Foot-pounds. And what else do we need with a moment? Direction. What is the direction of a moment? Rotation, right? It's either clockwise or counterclockwise. So if we're going around point A, I attach a little string to the arrow. I let the arrow go. It does that. Right? So that's clockwise, which is negative. I treat this like an arrow. You know what an arrow is? Shoot an arrow. I tie a string to the point. Tie a string from point A to the arrow. Let go of it. No, don't do that, Ben. We can do a moment about anywhere, but we don't want to do a moment about 4 different places at once. What about point A? You're doing it at point A. So you focus on point A. Okay. If you could do it at B, but we didn't choose that. The book didn't choose that. So when you choose a point, you got to stay there. Don't be jumping around. And don't be what ifing. It's not good strategy. What if you could be here 40 hours? All right. So yeah, tie a string to it, let go of it, it rotates. Then think about a clock, like, oh, is it going the same way as a clock or is it not going? I mean, you'd have to know, like the old school clock, right? That actually has a arm going around it, which we don't do anymore. There used to be a clock there, but oh, it's over there laying down now because it's dead. Anyway, that's how I do it. I attach a string to the arrow, let go of the arrow. It's going to swing one way or the other, right? And that's clockwise. The rule is clockwise is negative. I can't tell you why that. I really can't tell you why that's a rule, but that is a rule. Okay. All right, let's do the 40. So that's the 20, because I can see it in my notation. So now I'm going to do the moment of the, I'll just do moment A of the 40. That's probably the right way to write it. What's the force? 40. Don't overthink this. What's the distance between the 40 and A? 9. 9 feet, right? Attach the string to it, let it go. Which way is it rotating? Yep. 4 times 9 is 36. Add a 0, 360, right? Foot-pounds. And then the rotation is this way, negative. Yeah. It's not difficult when it's all vertical. So don't make it difficult. Oh, sorry, not summing yet. Moment about A of the 50. That's this one. What's the force? Yep. 50 pounds. What's the distance? From here to here is 6 and 5 and 4, 15 feet. Yeah, counterclockwise. 750 is the number. And this one, tie string to it, let it go. It's going to rotate around that way. That is counterclockwise or positive. And the last one. Moment about point A of the 30. What's the force? 30, whoops, pounds. What's the distance? Yeah, whatever, all this added up, right? So 15 plus 8, 23. 30, 23 times 690 foot-pounds and rotation. Clockwise, negative, thank you. So moments are very specific to a point. Choose your point, stay there, right? It can be any point, but for now they're choosing for you, which might be a good thing. Just don't change your points. You can't do one force moment at A, another force moment at B, another force moment at C. You're getting nothing. Like you're not collecting anything. Too many locations. All right. So the second part of this said, compute the algebraic sum of the moments with respect to point A. Be sure to note the sense of the resultant moment. So they're just saying, hey, now that you've done all these moments about point A, sum them up. Okay. So we have a negative 80. That's in. We have a negative 360. That's in. We have a plus 750 and a negative 690. Negative 380. So the sum of the moments about A would be negative 380 foot-pounds. Right? Summation moments A. That's just adding them all up. That's it. That's all this problem wanted. So the rest of it we did in class was adding all the vectors, because really what you've done is you've taken all these vectors and moved them to A. You've done that by collecting their rotational effect. All right, that's good. Let's move on to 24. Which is one of your homeworks. Compute the moment about point A for the linkage shown. So, moment about point A is what they want of this 2K force, right? I know that moment is equal to, what's that equation? Force times distance, right? But it's the perpendicular distance. And this is not, the 2K is not 90 degrees to this pole. It's actually 70 degrees, right, from the pole. Or if you look at this side, it's like 110. But it is not 90 degrees. It's not perpendicular. Agreed? Yeah. So we cannot use the 3. We can't just say, oh, it's 2K times 3. It's not perpendicular distance. Where is the perpendicular distance? Well, I'm going to extend my line of action. And I'm going to find the perpendicular distance. It's here. So this is the perpendicular distance that goes in force times distance. Right? These were easy. They're all perpendicular distances. We just use them directly. This one's not as easy because I don't know the perpendicular distance. I know this is 3 feet. I know this. I can probably find some angles, like this angle here would be what? Yeah, it's 180 for a straight line. Take away 110, it's 70. Right? So now I know 70. I made this perpendicular, so that's 90. So then I could get this if I really wanted to. It's 20, right? 70, 20, and 90 make 180. But what I want is this, the perpendicular distance, because then I can put it in my equation and solve for the moment about A. How many degrees are inside a triangle? 180 inside a triangle. So you have a lot. You have the hypotenuse of 3 foot. You have all the internal angles. You can use pretty much any function except for tangent, right? To get this perpendicular. What do you want to use? I want to make it green. That's the important distance. Sure. Thanks. We can use cosine 20.
That distance. that
This is telling me I have to know the perpendicular distance for the force. The force is the 2K, Ben. So then all I did was I took the 2K line of action and I made it really long. Right? There's the line of action. And then I said, okay, here's my point. Right? That I want the moment about of this force. So I got to find the perpendicular distance. Where is that? It's where this line makes 90 with this line of action. And the equation's telling me that. Like it's got to be the perpendicular distance. It can't be just any old distance like 3. 3 is not perpendicular. So I found it. I created this distance and said, okay, that's 90 degrees for that line. Therefore, this is the perpendicular distance. Okay, that's how I did it. There's other ways, but this is the first way. This one's pretty straightforward. It just uses the trig that we're getting a little more comfortable with. Adjacent over hypotenuse 3 feet. Perpendicular distance equals 3 feet times the cosine 20. 2.8191 feet. So now I can do my moment because I know the perpendicular distance. The force is 2K. The distance is 2.8191 feet. I have a moment of 5.64. Sorry. All right, 2K times this new perpendicular distance, 5.64. Kip feet. Kind of an interesting unit. Kips are pounds, thousands of pounds. What kind of rotation do I have? Take a string, tie it to the arrow, let go of it. Where's it go? Yeah, it's going to go this way. Right? Clockwise, which is negative. This is a big concept. Like perpendicular distance. Big. Like we have to really understand that, hey, to get a moment, I've got to know this perpendicular distance or I have to have some other strategy. So. These can be like, first, any questions on that? Like, that was a lot. But when you have forces at angles, the perpendicular distance, you have to find that, okay? You can't just guess, and you can't use numbers directly unless it's a parallel system like this, like perpendicular, right? Those are easy. Not perpendicular, not as easy. I got to find it. Yeah. Yeah, there's only one force. What's with the negative feet?
So when you got the moment, it was like negative 5.64 K minus 2.
Kip feet. That's how you write kip feet. So it's like these were foot pounds, right? So you can write those foot pounds. Sorry, that does look like a negative, but I'm just really putting the two units together. If you just write it like this, that's kind of weird. Like that's not common. So you could write it like foot right? Foot times pounds, because it is foot times pounds. I tend to do this kip feet, so. Yeah, sorry about that. A little weird notation. So just to hammer on that a little more. If you have forces at an angle, we don't really need a lot. Right? We don't need a lot of information. You can just do it graphically. You know, if this was 20 feet and this is 10 pounds, and I want the, and I'll say that's 50 degrees, and I want the moment of the 10 pounds about point A, is the 20 feet perpendicular? Is that the perpendicular distance? No. Definitely 20 feet is not perpendicular to the 10. Where is it? Extend the line of action and make perpendicular from A to the line. Well, it's not down here. That doesn't make perpendicular. Perpendicular means make a 90 degrees, right? So kind of just graphically, I can say, oh, I guess I could use my triangle, right? And slide it along here. And that would be the 90-degree corner. There's 90 degrees. There's perpendicular. Right? So, I mean, you can play this game over and over and over. Just draw a line. Put in some crazy angle force. That part, right? And here's my point A. Where's perpendicular? Got to make 90 degrees from A to this vector. Very hard to do unless you extend their lines of action. Like, just get their lines of action in nice and long. Want those intersecting, right? And then say, where's 90 degrees from A to my line of action? It's right there. Perpendicular distance, force. Right? What if I had one more? What if I had this? Point A, and here's my force. Yeah, the distance is going to be 0. There is no perpendicular distance. So this force, is it creating any rotation about point A? Nope, it's 0. Okay. What if there was 2 forces here at my point B? Is this one creating moment about point A? Absolutely. How much is it? 800 times 10. Yeah, assuming this is straight up and down, right? 800 times 10, 8,000 foot-pounds of rotation about this point. That makes sense? Check this out. Just going to build my little box. Yeah. What if I had that force in? Hang on, I'm going to calculate it. And it is 894 point, that's pretty fun. Yeah, so what if these two were not here? And I just had the 894 force, right? And I wanted to know the moment. Well, we've been talking about, oh, I gotta extend this line of action. Find the perpendicular distance, which is right in here, right? That's how I could do it. 894 times this distance gives me the moment about point A. But the other way to do it is turn 894 into its components and find the moment of that and the moment of that.
If you were to do
Exactly the same. Yep.
it would be 894 squared, and then you get the number that was inside of the actual square root.
This 894 is this vector. Yeah, you wouldn't square it. If you're going for the 400 and the 800 from the 894, you'd have to use trig. You'd have to use trigonometry to get the components. So this is actually a theorem. It's Vergenon's theorem. Not that we need to remember that, we don't, but this dude basically come up and said, hey, we want these kind of things, right? We want to know the moment of this vector about that point. We can do it like this. We can find the perpendicular distance, multiply it times the vector, and we have the moment, right? We've done that. But he said, you can also turn this vector into its components, get rid of the vector, and then find the moment of each one of those, and it'll be exactly the same. Which makes sense because these two components are exactly the same as that vector. They replace it. So a lot of times this system is easier. Find the components, then find the moments of the components. It's the same exact process. Okay. All right. We're not quite there yet, but I saw that as a good opportunity. One more and then we'll take a break. This one. 25. This one's tricky because it's hard to find the perpendicular distance. Like if they want the moment of the 150, which I'm guessing they do, compute the moment of the force about point A, the condition is shown. And then they didn't give you any measurements to anything down here at point A. So you just had to assume that it's 20 feet up to wherever this force is, and then it's 5 feet over. So that's all you can do with the problems they give you, and they don't give you any depths or anything. So yeah, it's tricky because if you want the moment, one more time, what's the moment equation? Force times distance perpendicular. So I tried to draw this kind of graphically accurate. And now I'm going to extend the line of action. Right? And then where's the perpendicular distance? It makes 90 degrees with that line. It's right there. Agreed? Perpendicular distance. How am I going to find it? Yeah, so you just got to do some triangulation, right? And what I do is I draw from here to here. Because I know this is 20. I know this is 5. Correct? And I could get this. I'll call it C. This is the perpendicular distance right there. Yeah, I don't know. I wouldn't make that assumption that it's just two exactly the same triangles. It might be. I just wouldn't go there. I know this is 60, right? Out here. But that's kind of all I got. Yeah. All I got. I know this is 90 right there. So if I can start getting, I know this is the 150 here, but that's in pounds. Should write that in a better spot. Try and keep this as clear as possible. This is 150. But that's pounds, and I have feet over here. So you have to be careful with what you use. These are feet. I can find angles, right? I know we're 180 right here. That straight line is 180, right? So if I could find this angle, theta, I could take it from 180 and 60 from 180 and give me my inside angle right there. That'd probably be my strategy. Because this is a right triangle and I know one side. So if I could get this angle, I could start to work towards this, I think, with tangent. So can I get this angle? Sure. Tangent equals what? Tangent of this angle is opposite over adjacent. 20 over 5, theta equals. $75,963.6. Now I can go for this angle. I'll call it alpha. So alpha is going to equal 180 for the interior angles, or excuse me, 180 for a straight line, minus 60 minus 75.9636. Alpha equals 440362. Now we have that angle. And we have the 150 pounds. And we want this perpendicular distance. So actually the 150 pounds is not helping us yet. You can find this, right? Yeah. In feet, because we need this in feet. So how do we get this? Yep, Pythagorean theorem, the 20 and the 5, right? So C equals square root of 5 squared plus 20 squared. $20.6155. I'm gonna do that again. Okay. Seems tight, but yep. All right, now we have this and our angle, and we can get this. So it looks like it's opposite, should be sine 44.0362 equals perpendicular distance over 20.6155. Perpendicular distance equals. $14. 33 feet. All that just to get that perpendicular distance. All that, like, that's a lot. But we needed that to run this equation. So moment at A. There's only one force. I could write of the 150, but I don't need to. There's only one force. 150 pounds times the perpendicular distance, 1433 feet equals 2149.51 foot pounds. And which way does it rotate about point A? Yeah, tie a string, let it go counterclockwise, which is positive. Excellent. So that's a lot of work to find the perpendicular distance, a lot. Varaganon said, hey, you don't have to do all that work. That's a lot of work. There's another way to do it. Take that vector, turn it into its components, X and Y, and then do the moments. Why is it easier? Well, what's the moment of this force times A? Force times perpendicular distance, which is right there, for that force is what? It's 5. The moment of this force about point A, perpendicular distance, is right here, 20. They're easy to find. You got to find the components, which is a little trigonometry, but Varaganon said, hey, that's way easier. Turn forces into their components, find the moments of the components. So that's the other way to do it. All right. Break time. You need it. I need it. I'm going to pause the recording. We're going to come back and do it by comp. Same problem, but this time we don't go for the perpendicular distance. Varaganon said, hey, you can take this force, turn it into its components, and nothing changes. Like it's the same effect, right? So they gave us 60 degrees. So this was chapter 2. We said, hey, we can find the components of a force. No problem, right? I know there's one, and it's got down effect. So there's definitely a down effect, Fy, and it has X effect. So there is a X, Fx. And Varaganon said, you can get rid of the 150, put these two in, then your distances for the moment is a lot easier, like way easier. So that's what you do is you say, okay, I'm going to get rid of the 150. That means I got to put in the Fx and the Fy. That means I have to draw that triangle. So however you want to draw that triangle is good, right? You can go like this and this. Here's X and Y, and then the 150 is always staying in position. 150, right? And then this is Fy, this is Fx. So those are the components of the 150. Shown here and here, because it does matter where, where they apply. They apply there at that tail. Now I just need to use my 60 degrees somehow. So that's down here between horizontal and the force 60. That up there would be what? 30, and this is 90. So find the components. We can use pretty much any trig function except for tangent. So I could say, let's see, sine of 60 would give me Fy. Opposite over hypotenuse, right? Cosine of 60 would give me Fx. So Fy equals Fx equals, well, this is chapter 2 stuff. We had this down at one time. So the Y effect going down is 389.71 pounds. And the X effect going this way to the left is 60 and cosine 150 times 75. So those are the two effects. Fx 75. Fy 389.71. Uh-oh.
Yeah.
Which one did I screw up? Fy. Sine 60 times 150? Yeah, 129. Good catch. Thank you for calculating. $129.9. That's why we don't work in pen. You can't erase it. All right, we found the components. So whenever you find components, that means that this 150 can go away. It's no longer there. My finger's hiding it. Right? It's gone. The components are in. The 150 is gone. That's important because it simplifies the problem. All right. So now with this gone, Verganon said, hey, the moment's going to be the same, just use these components. So now I just have to sum the moments at A. And it is summing because now there's two vectors instead of one. We got to get the moment for each vector, right? So let's do the X first. Extend its line of action way out here. Where's perpendicular of this line with point A? Right here, perpendicular, 20 feet, right? So it's 75 pounds times 20 feet, force times distance perpendicular. What's its rotation? Again, we're completely focused on the 75, on that force right there about that point, and that's all you look at when you're doing a moment. Yeah, tie the string on, you let go, it goes like this, right? It goes, careful. Which way is that? Is that counterclockwise? That is counterclockwise, yep. So it's a little difficult when they're out here away from the point. So remember, you can move it anywhere. So go ahead.
We'll find out that it's going at force of X is going to the negative direction.
Negative direction doesn't give you rotation. You need rotation. Yeah, it's different. Completely different because clockwise is positive rotation, right? So I move FX here. I attach the string. What's it do? Goes that way, which is counterclockwise, which is positive. So this is a positive moment. Yeah. Rotation's totally different than translation. You're right. This force is pointing in the negative direction. You're correct. But that's X and that's, X direction. That's not rotation. Rotation is this. All right. Excellent. Now we got to do FY. We don't look at anything else. We just look at FY. We draw its line of action, nice and long, right? And find the perpendicular distance right there. That's the perpendicular distance. 5 feet, exactly. So it is 129.904 times 5 feet. Now I need the rotation. So I'm going to take FY, I'm going to slide it right down here. I'm going to put it there. Tie a string, yep. And it goes positive. This is feet plus. So we have this moment doing this. We have this moment doing this. They're both positive. Our work is done. Moment at A equals. Not quite done. We got to go 75 and 20 and then 129.904 and 5 and we add. My moment 2149.52 foot pounds rotation counterclockwise. What was it in the last problem, the way we did it? 2149.51. 2149.52. That must be rounding. Otherwise, it would be spot on exactly the same. This one, the first one, I call it the formula, using the formula directly. We found the perpendicular distance in this one, right? This one is finding the moment by components. Two different ways to do it, exact same moment, exact same effect, if we don't muck it up, which me almost did. That would have been bad. Okay, that's Verganon. If you come up with something like that, they'll name it after you. That's cool. Be the Danner Hamburg? How do you say your last name? Hamburg theorem. The Danner-Hamburg theorem of moments. He's like, just let me out of this class. I'd like to go hit a baseball. It's like, no, I'm done with that too today. So, all right, that's it. What you have some, let's go one more share here. New share. Back to this share. Back to the calendar. What are you going to do? You're going to do 26 and 27. Moments. Chapter 3 goes on forever. 26 and 27. Oh, I have to do another new share. All right, I'm kind of into the sharing thing today, so there we go. Share. That's these two. So parallel systems, and I believe you're going to find the moment about a point, and then you're probably going to find the resultant. Yeah, resultants of parallel force systems. So you got that. No problem. See you Wednesday. We'll do more. We're close to done with the content of chapter 3. But if you look at this chapter, there are a few chapters in the book that give you 74 problems to work. So actually 75 problems in this chapter? Yeah, so this is a chapter they really want an instructor to emphasize, like make these students do a lot of this so they get it. Because we're gonna use it all flipping for the next 6 months. So there you go. All right, go away. Be good humans.